I'm Eryn.
And I'm Aspen.
And I'm Amy, and our project is the Internet of Things window controller. The goal of this project was to open and close a window with feedback using the particle photon Internet of Things so that we can change the set point through one of our phones.
The best method of describing a circuit is by dividing it into subsystems. This system includes 4 subsystems. The first subsystem is the photon Wi-Fi enabled device created by Particle. This programmable device connects to a phone app, allowing for inputs to be observed and outputs to be controlled remotely via smartphone. Its purpose in the setup was to send a set point to a microcontroller. Subsystem 2 utilizes a microcontroller to convert inputs into desired outputs using code. The microcontroller creates the up and down signals for the DC motor based on comparisons of the set point and feedback voltages. More on this feedback signal later. A deadband or tolerance window added to the programming prevents the motor from running back and forth, attempting to hit the set point exactly. This phenomenon is known as hunting. Once the internal logic of the microprocessor determines the appropriate up-down signal, that signal then travels to subsystem 3. In subsystem 3, the outputs from the microcontroller are then fed into an H-bridge circuit. An H-bridge is an integrated circuit that uses internal transistor switches to reverse polarity of the current across the device connected to its outputs. These transistors are activated by applying a voltage to the corresponding input. When the input signal is sent to the H-bridge, the 2 switches allowing current to flow across the DC motor in the forward direction are closed. When the down signal is input, these 2 switches are opened, and the 2 allowing current to flow across the DC motor in the opposite direction are closed. This lets the current reverse the direction of the motor accordingly. This subsystem also produces the feedback signal that was fed into the microprocessor. The DC motor is mechanically linked to a variable resistor. As the window is moved, a contactor is moved along the resistor, increasing the voltage drop across the resistor as the window closes. The leftover voltage is connected back to the microprocessor. This feedback voltage changes linearly with the window position and can therefore be interpreted using the program to indicate when the window has reached its goal set point. The final parts to be discussed are the safety features built into the overall system. As the DC motor reverses polarity, residual current can cause damage to the system. To protect the circuit, 4 diodes are added to allow any residual currents to travel to ground. The other protection devices added are 2 switches with diodes connected across them. These switches are opened mechanically when the window moves all the way up or down and cut power to the DC motor. The diodes allow power to flow across the switch when polarity is reversed to move the window in the opposite direction. These devices help protect the circuit and protect the overall mechanism from being damaged.
First, we set up the photon using the app on the phone and confirmed it was connected to the internet using the Tinker program that comes already on it, which allows you to turn on and off the onboard LED. And of all of the analog outputs to determine which one we wanted to use, we decided on the one that changed voltage rather than the duty cycle. Then we connected it to the embed, H-bridge, and a small DC motor to confirm that it would function as desired when we changed the set point on the phone. Throughout this process, we used the analog discovery kit as our oscilloscope whenever we wanted to look at the signals, and we also used it as a 3.3 and 5 volt power supply during early testing and setup. Next, we took the system that we had created and combined it with parts of the existing analog system that was already connected to the window. We replaced the analog input signals with our embed and photon, and then took our up and down digital output signals and put those into the H-bridge that was already set up with the higher voltage for the motor. We also took the power supplies that were already part of this system and use them to power our devices.
Here, the set point of the system is being changed from the particle photon app. The set point was decreased, causing the feedback of the motor to become greater than the upper limit of the system. The forward output on the H-bridge turned on as a result and moved the window back into the accepted range. In this case, the window closed completely. This time, the set point was increased, which caused for the feedback of the motor to become lower than the lower limit. The reverse output on the H-bridge turned on and the window opened until the feedback was back in the accepted tolerance of the set point.
This setup demonstrates how an electrical system can be controlled remotely through a Wi-Fi enabled microcontroller. While this circuit was not particularly complicated, more features could easily be added. Examples could include light and temperature detection that would close the window at night or when temperatures become too hot or cold. Furthermore, while this setup uses an input directly from the user via smartphone to open or close, another photon device could be attached to communicate remotely to the one already in the system. Having multiple components in a system communicate wirelessly to complete a desired task is the basic principle behind the phrase Internet of Things. We hope that you enjoyed our video and that this information inspires you to build your own Wi-Fi controlled circuit.